Welcome back to mathkernel. Last time we saw everything an orthonormal basis buys you, coordinates and lengths for the price of a scalar product. But we assumed someone handed us that basis. Today we stop assuming. We take any basis at all and manufacture an orthonormal one, with a single formula that doesn't care whether your vectors are arrows, polynomials, or matrices. Here's the whole method in one line. Keep the first vector as it is. For every vector after it, subtract off its shadow on everything you've already built, and what's left is perpendicular to all of them.
So on the board, V2 leans toward V1. You drop it straight down onto V1, that violet piece, and the leftover W2 stands at a right angle.
Exactly that. The shadow is a projection. The amount of V2 that already points along W1 is the scalar product of the two, divided by W1 with itself. Subtract that multiple of W1, and the remainder can't have any W1 left in it.
Hold on, why divide by W1 with itself and not by its length? That denominator always trips me up.
Because W1 isn't a unit vector yet. The projection coefficient is the scalar product over the squared length. That's W1 with itself. If W1 happened to be unit length, the denominator would be 1 and it'd vanish. We don't normalize until the very end.
So length 1 is the last step, not the first. Same lesson as last time.
Same lesson. Get the right angles by subtracting projections, and only then rescale each survivor to length 1. And crucially, the span never changes along the way. So Schmidt is one move repeated. Take the next vector, strip off everything parallel to what you've got. Keep the perpendicular remainder. Let's prove it actually does what I claimed. Two things to check. The span stays the same, and every new vector really is orthogonal to the earlier ones. Both go by induction.
Span first, why is that even in question?
Because each W is V minus a combination of earlier W's, so Wm lives in the span of V1 through Vm. But you can also solve that backwards for Vm, so nothing is lost either way. Same subspace at every step, cleaner set of vectors. Now orthogonality, and here's the move you'll recognize. Take the new Wj, it with any earlier Wk, spread the scalar product across the sum. Exactly like the Fourier trick last time.
And I'm betting most of those terms collapse.
All but one. By the induction hypothesis, W1 through Wj minus 1 are already pairwise orthogonal, so every Wi dotted with Wk is 0 except when I equals k. That single surviving term cancels the first piece exactly. You're left with 0.
So the whole sum was engineered to kill the one direction that would have spoiled the right angle.
Precisely engineered. And since the span is full, none of the W's can be 0, so they form an honest orthogonal system. Normalize, and it's an orthonormal basis. So span-invariance keeps the vectors legitimate, and the step identity forces the right angles. The same Kronecker collapse, doing the work again.
Before we grind an example, does this process ever get stuck? Is there a space where you just can't build an orthonormal basis?
No, and that's the first payoff. Any finite dimensional space with a scalar product has a basis to start from. So run Schmidt on it, and you always land an orthonormal basis. Existence, for free, though it's never the only one.
So the mere fact that a basis exists guarantees an orthonormal one exists.
Right. And there's a sharper version. Suppose you're already handed a partial orthonormal set, say 2 perpendicular unit vectors, and you want to grow it into a full basis without disturbing them.
But Schmidt rebuilds vectors. Won't it mangle the ones I want to keep?
Here's the lovely part. It doesn't touch them. Extend to any basis, then run the process. For each vector that's already in your orthonormal set, all the projection terms are scalar products of perpendicular vectors, which are 0. So it subtracts nothing, and normalizing a unit vector changes nothing. the first k come out identical.
So the process only ever works on the new vectors and quietly leaves the good ones alone.
So every space has an orthonormal basis, and any orthonormal start you already trust survives the extension untouched. Now the reason this one formula is worth so much. Look at what it actually asks for: scalar products and norms. Nothing else. It never mentions coordinates or arrows or anything specific about the space.
So the same formula runs no matter what the vectors actually are.
As long as you have a genuine scalar product, yes. On Rn, it's the dot product. On polynomials, it can be an integral of p times q against a weight. On R4, it might be a general bilinear form given by a matrix. On matrices, it's the Frobenius product, the trace of A transpose times B.
Come on, integrating two polynomials as a scalar product, and Gram-Schmidt still just works. That feels like it shouldn't.
It works because the proof only ever used the scalar product axioms: bilinearity, symmetry, positivity. It never peeked at what the vectors were. Feed it that integral, and out come orthogonal polynomials, the Laguerre family, in that particular case.
So the skeleton, compute the bracket, subtract the projection, normalize is identical every time.
Word for word. The only thing that changes is the arithmetic inside the bracket. Write down which scalar product you're using, and the rest is muscle memory. So it's one procedure in 4 disguises. Pick the right bracket, and the exact same 3 moves do the rest. Let's ground everything in one honest computation with the standard dot product. We want an orthonormal basis of the kernel of a 2x3 matrix A, a plane sitting inside R3. First, the raw basis. The second row of A is just -2 times the first, so there's really one equation. Solving it gives 2 integer solutions, -3, 4, 0, and -1, 0, 4. Those span the kernel.
And they're close to perpendicular already, but not quite, so we run the process inside that plane.
We do. Keep W1 as the first vector. Then V2 dotted with W1 is 3, and W1 with itself is 25. So W2 is V2 minus 3/25 of W1, which tidies up to 4/25 times -4, -3, 25.
Prove it's actually orthogonal before you celebrate. I don't trust fractions.
Fair. Normalize both. W1 has length 5. W2 has length root 650 over the scale, and the 2 unit vectors. You get 12 minus 12 over the norms, which is exactly 0. Perpendicular, confirmed.
So 2 clean unit vectors, and together they're an orthonormal basis of the whole plane.
So find a basis, subtract 1 projection, normalize, check the bracket is 0. That 4-beat is every Gram-Schmidt problem you'll meet. Let's gather it. Gram-Schmidt takes any basis, subtracts earlier projections to make it orthogonal, then normalizes to make it orthonormal, one formula, applied down the list.
And because it always runs, every finite-dimensional space has an orthonormal basis, and any orthonormal set you start with survives untouched. Fine, but the whole thing leaned on knowing the scalar product. Where does that actually come from when it's some abstract bilinear form?
That's exactly the next thread. We've been handed scalar products. Next time we ask how a bilinear form gets encoded as a matrix, the Gram matrix, so you can compute one from scratch. So, Gram-Schmidt earns you a perfect basis. Next, we learn where the scalar product itself is stored. That's the Gram-Schmidt process. Subtract the projections, normalize at the end, and any basis becomes orthonormal under any scalar product. Thanks for watching. That's everything ready in this chapter so far. More on the way.